how's it going? Today we're going to be talking about equilibrium. Now this is specifically mentioned in the OCR A spec at A level, but actually if you're doing either AQA or edXL, this is also going to be super useful to you because it's still physics that you are taught, it's just presented in a slightly different way. And one of the great things about understanding a topic really well is that you can understand it even if it's presented in a little bit of a different way. So this video is probably still worth a watch. So the first thing we're going to talk about is what objects in equilibrium are. So if an object's in equilibrium, it means it has no resultant force acting on it, which means that it's either stationary or at constant velocity. Now this is a thing that always trips up students, is they always forget that an object can be in equilibrium when it is moving. If it's at constant velocity, it can still be in equilibrium. Because remember back to Newton's first law, an object that's got no resultant force acting on it will either be stationary or at a constant velocity, because objects will continue in the same state of motion until a resultant force acts on them. So if an object is already moving, it needs a force to slow it down. Now, in reality, in the world that we live in, we don't think of objects as being like that, because if I'm driving my car at 70 miles an hour and I take my foot off the accelerator going down the motorway, I'm going to slow down. But that's because what we can't see are the invisible forces of friction and air resistance that will be acting on my car as I drive it. So Newton's first law is a little bit unintuitive. We need to make sure we keep going back to it when we're talking about equilibrium. So we're going to look at a basic example that I've got here with an object. So this object's in equilibrium. We know that it's being supported by 3 Newton tension forces, and I need to work out what the weight is, okay? So what I need to think about is the fact that actually there has to be no resultant force acting on this object. So if I were to break these forces down into their resultant vectors, let's see if I can draw a better right angle, there we go. I know that this force has to equal this force, and I know that these two forces here added up have to equal the weight. So it's going to be in the vertical plane that I'm going to have a look at to help me resolve this problem. Okay, so I need to figure out an angle, so I'm just going to put this one here as 60 degrees. Because that's going to help me just so that I can make this diagram clearer. You could also work out using 30, you could work out this one, but I don't like to do that. Now the reason there is that because I've got to consider the upward forces acting on both pieces of string. If I drew my triangle going into the middle like this, it'd be really easy for me to think that there's only one force acting upwards on this box. There's not, there's two, because there's 2 pieces of string. So I'm going to change it to be over here, but you can use it that way, and if you're better than me and you do it correctly, then fantastic, you'll still get full marks for that. So I need to work out what this component of the force is. It's going to be the opposite. So if I remember SOHCAHTOA, I've got the hypotenuse, which is 3 newtons. I'm going to try and find the opposite, so I'm going to use sine. So sine of 60 is equal to the opposite over the hypotenuse, which is 3. So 3 sine 60 would give me the opposite. So where is my calculator? 3 multiplied by sine of 60 gives me 2.6 newtons. Now, because these strings have got the same angle and they've both got the same force in them, this upward one here is also going to be 2.6 newtons. Now I know then that 2.6 plus 2.6 is going to equal the weight acting downwards. This is where we're bringing in my principle of equilibrium, because I know that if this object is stationary or moving at constant velocity, so it's in equilibrium, that there has to be no resultant force acting on it. So the upward forces on the object have to equal the downward forces on the object. So the 2.6 and 2.6 acting upwards have to equal the forces acting downwards, which is the weight. So 2.6 plus 2.6 will give me the weight. So the weight would be 5.2 newtons. Now, there is another way of solving problems like this, and this involves using what we call a force triangle. So if an object is in equilibrium, if we draw all the forces on it as like a vector diagram and put all the vectors tip to toe, like we did at GCSE for resolving forces, then actually all of those arrows should join up to make a complete triangle. So if I were to draw this diagram out as a vector triangle, I'd measure my 3 newtons at the right angle here, so that'd be 30 degrees. I would then move this arrow so that we're tip to toe. So we're going to take this arrow, move it up like that. And again, I would measure it so that it's the same length as this arrow because they're the same amount of force. So remember that when we're doing a vector diagram, we use the length of the arrow to denote the size of the force. So I'll draw it again, something like that, 3 newtons. And again, I'd try and make sure that I'm using a protractor. So I've got the angle here, correct? And then I can just join the top of this vector to the tip of this one I'm going to use a different colour to make it more obvious, like that. If they form a complete triangle, that shows me that we are in equilibrium. A complete triangle means equilibrium. So I could actually even use this method to work out what the size of that weight's got to be, because I could measure the length of this arrow and then use whatever scale I did. Let's say that I used 2 centimetres as 1 newton. I'd measure the length of this arrow and then I could convert it back into the size of a force. So this is a really key skill if you're thinking about equilibrium that can be really useful. It can make some questions a lot quicker, and actually sometimes they ask you specifically to solve problems using this method here. So let's do another example. So let's say that I've got an object and it's got 3 forces acting on it like this, and I want to find out if this object is in equilibrium. All I need to do is just draw the forces to scale at the right direction into a triangle. So I'm going to put the vectors tip to toe. So this vector, I'll start with that one. I'm going to move this one so that's on the top there, like that. This one comes in here, and there we go. If we join up to make a completed triangle, then we know that the object is in equilibrium. If, for example, this object wasn't in equilibrium, let's draw something like that. So I'll change this one here. So that would go then onto here, so like that. I could use this method to work out what the size and the direction of the force to make this object in equilibrium is needed. So I could just square off the side of this parallelogram. So I'd need to add a force in that direction at that angle of that size to make this into an object in equilibrium. Now, I do really hope that you found this video useful, and I hope that you're thinking that these are going to improve your physics grades. But if you really want to improve your physics grades, I think the best way to do it is to have a look at joining my live lessons. So check out the link in the description of this video to see if you want to join up. Now, whilst you're there, check out the link of this video. You could also remember to subscribe to this channel so I can carry on making more videos like this. And don't forget, if you want the notes for this topic, to check out my resources on the My Edspace website. I'll see you next time.